Hello and welcome everyone. In this video, I'm going to continue talking about network effects, but with a different version of our demand curve. So in the part one of the lecture, which is network effects in platform markets, there we're thinking about modeling the network effect, be it positive or negative, directly into a standard demand curve. Here, I'm going to introduce a new quadratic demand curve. So just to recap, when we're thinking about a network externality, we're thinking about goods for which the number of consumers in the market is going to increase or decrease the valuation of each individual's consumer for that particular product. So we'll think strictly in terms of positive network externalities for the duration of these slides here. Basic idea is you think of a situation where you have some product, you've got some valuation for it, but as more people join and use the same product that you can now communicate with, then the valuation for that good is going to increase, such as with email. Well, I say here email is useless if you're the only one with an email account. That's not literally true. I like emailing myself stuff so that I've got it. I don't necessarily trust some of the cloud and Dropbox type stuff, so I like emailing myself a lot of stuff, but definitely email is more useful if there's more people with email. So that's the direct effect. Then there's an indirect effect. So you think of like the old example of video stores. A video store is not going to locate in an area if nobody has videos. On the other hand, you don't want a video player unless you can buy them. And so there's this sort of indirect effect relative to the network externality. The basic idea is we're thinking of a situation where one person's valuation depends on the number of others with that good. All right, so here's going to be our setup, ultimately beginning with a standard downward sloping demand curve and building to our quadratic demand. Suppose we've got 1,000 people in a market arranged according to their valuations. So your order in the distribution is just your reservation price. So first person has a valuation of 1, reservation price of 1, and the last person has a reservation price of 1,000. They're the one who's got the highest willingness to pay. So if the price of the good is P, the number of people who think the good is worth at least P is going to be 1,000 minus P. So if the price is 200, 800 people are willing to pay $200 or more. And then the total amount that we would sell if people buy at most 1 unit of the good is going to be 800. And of course, this is a standard downward sloping demand curve, right? Q is equal to 1,000 minus P. All right, now let's add in a network externality, and suppose the valuation is going to be a product of my own willingness to pay and N, where N is the number of consumers. Therefore, the more people who consume, the more each is willing to pay to acquire the good, because I'm going to multiply my reservation price by the number of other people in the market, and my overall willingness to pay will rise. What happens to our demand function? Well, we need a little bit of work here. So let's call V hat the consumer who's exactly indifferent between buying and not buying. That person's willingness to pay is just P. They're the person who's indifferent between buying and not buying at that price P. So we'd say P is equal to V hat, which is their reservation price, times the number of people who are currently buying. V hat is the person indifferent about buying, so everyone with higher values for sure buys. So the number of people who want to buy is then going to be N is equal to 1,000 minus V hat. So if V hat is the person with a reservation price of 200, right? N is equal to 800 because 1,000 minus 200 people have a valuation of 200 or higher. All right, now we can combine these equations though. P is equal to V hat N and N is equal to 1,000 minus V hat. And we want to get this as an inverse demand, price in terms of quantity, where quantity is going to be represented by N, like the number of people buying. So what I need to do to make this happen is I need to say, all right, well, I can solve this for V hat. This is going to be V hat is equal to 1,000 minus N, and then just drop this into my equation. Right? So solving for V hat, solving this thing for V hat, this will be 1,000 minus N, and then substituting for V hat here gives us this. Now I realized I did a couple things. First off, need to actually write this out as V hat is equal to 1,000 minus N. Also, I've got V hat N, and here I've got N times V hat, right? 1,000 minus N. But anyway, you can see if we, with some manipulation, we can substitute this into here and get this. And that is indeed a demand curve, right? It gives the relationship between the price of the good and the number of users. With the number of purchasers on the quantity axis, as would be standard, and the willingness to pay on the price axis, as would be standard, we have a demand curve, but it's quadratic, right? It's going to be quadratic because you're going to have an N squared. N times, you have 1,000 N when we distribute, and then minus N squared. As a matter of fact, it looks like this. It's going to be this downward opening parabola, And look what's happening here. We've got 3 equilibria labeled. What's going on here? What are these arrows doing? Well, our willingness to pay is on the vertical, our network size is on the horizontal. And what I like doing, boy, if I had the chalkboard here, what I would like doing, maybe I can still make this work out here in this session because I had forgotten that I like doing this, is I like writing out the marginal benefit. I wonder if this will copy. So what I really need is for this to copy. Oh, it will. Okay. So I want to compare my marginal benefit to my marginal cost, right? So the marginal benefit is given by the demand curve. The marginal cost is given by the supply curve. And if we're back here, the marginal benefit's down here. If we're over here, the marginal cost is up here. On this side, this is my marginal benefit. And right here, whoops, on this side, this is my marginal cost. This is my marginal benefit. Okay, so what's happening? We remember consumers want to buy whenever the marginal benefit exceeds the marginal cost. The marginal benefit is given by the height of the demand curve, the marginal cost by the height of the supply curve. You could just think of this as horizontal constant average costs equal to marginal cost. Over here, the marginal cost exceeds the marginal benefit, so you'd leave the network. Over here, the marginal benefit, the demand curve is higher than the supply curve, so you'd want to join the network all the way up to here, and then beyond this point, the demand curve is below the supply curve, marginal benefit is lower than the marginal cost. So what's happening is I drew this arrow indicating that if we're in this small equilibrium, our tendency is actually for the network to crash down to 0, for people to leave the network because the marginal cost exceeds the marginal benefit. And over here, for it to grow to the larger network size because the marginal benefit exceeds the marginal cost. Here we have so here we have an arrow going into the equilibrium. Here we have arrows going into this equilibrium telling us that the large network should be stable. Because over here, if somebody leaves, well, now the marginal benefit is bigger than the marginal cost, so we'll get somebody else to join back in. Over here, if we add somebody additionally to the network, the marginal benefit is bigger than the marginal cost, we'd expect them to leave, right? And so this will be stable, and this will be stable. This one right here, the small network size, should be unstable. This would be, I don't know, maybe this is like the old MySpace. Maybe this is the present Facebook, right? So the idea is you have a large, stable network. Think about it now. In 2020, probably virtually everybody who wants to have a Facebook account does. And if you sign somebody else up for Facebook, they might just never use it. Like think about, like I could sign up think about like aging grandparents, sign them up for Facebook. They're not on it. They're probably not going to use their account. They're probably going to leave, right? And so that would be the situation. Over here, this would be the situation where the network has collapsed down to 0. And this is capturing the logic that the small network size is probably unstable. You're probably going to get the small network is either collapsing to 0 or it's going to rise up to the large network and then be stable once you get a critical mass. So that's captured here. If the number who are in the network is low, the willingness to pay of the marginal individual is low because there's few other network users. If the number in the network is big, the willingness to pay of the marginal individual is also low. Why? Well, then if you have everyone else is in the market who's valued the network more highly is already joined, right? So we have low willingness to pay here and low willingness to pay here. Why? Because these people these are the people who just never adopt whatever is that network. These are people who just never join Instagram or Facebook or Twitter, right? And so they have low willingness to pay relative to what would be their cost. Here's the situation where people have a low willingness to pay relative to cost because the network's small. Now as the network rises, the network externality increases the valuation to everybody until it reaches the point where those who value the good more have already adopted. And now you're getting the people who value on the downsloping portion, you're getting kind of the more marginal consumers. All right. Assuming the supply comes from a constant returns of scale technology, the flat average cost line that I said, now we've got 3 types of equilibria: no consumers, small number, and a large number. Those are our sizes. Which type of equilibrium do we expect? Well, in each case, demand is equal to supply. Quantity demand is equal to quantity supplied at the equilibrium by a definition of equilibrium. Elsewhere, if demand is higher than the supply curve, if marginal benefit is bigger than marginal cost, quantity rises. When demand is smaller than supply curve, marginal benefit is lower than the marginal cost, the quantity should fall. So we get a no purchase equilibrium and a large network equilibrium that are both stable. The small network is unstable. This is unstable. The arrows are going out of it. This one is stable. It's a large network, and this one's stable. It's zero network. All right. So here's some examples. Suppose we have 9 consumers. Each needs to determine whether or not they will join a new social networking site. Consumers can be ordered in terms of their types. The first consumer is type 1, second consumer is type 2, and so on. Each consumer's willingness to pay to join the site is proportional to the number of other members. So if n is the number of consumers that have become members, the willingness to pay for type T is just n times t. Find the largest price such that there's 7 consumers that are least indifferent to joining. The largest price such that we have 7 consumers at least indifferent to joining. All right, so it's a worked example, so I'll go right through the solution. We are looking to the price equal to the 7th member's willingness to pay. If there's 1 member, it's type 9, right? So find the largest price such that there's such consumers at least indifferent to consuming. Let's see. If there's 1 member, the person who will join will be the person of type 9. They have the highest willingness to pay. If there's 2 members, the people who join are type 9 and type 8. Type 9 has a willingness to pay of 18 because there's 2 people. 2 times 9 is 18. Type 8 has a willingness to pay of 16 because it's their valuation of 8 times the 2 people in the network is 16. If we have 3 members, type 9, type 8, and type 7 are the ones who join. So their willingness to pays are 9 times 3, 9 times 4, and 9 times 7. If we have 7 members, the last one to join is type 3. This person has a willingness to pay equal to 21. So the highest price we can charge is 21. Can we get the 8th person to join? No, because the 8th person is going to have a reservation price of 2. With 8 people in the network, 2 times 8 is 16. That's going to be smaller than the price of 21, right? So the highest price such that we get 7 people joining is the price of 21. Here's another example. So this is actually using, this will be actually using our quadratic formula to solve. Sort of a review from algebra. So suppose we have 200 people in a market for some good. The reservation price is uniformly distributed between 1 and 100. Suppose we have V as the reservation price and the good exhibits network externalities. For example, let us suppose the value of the good to person V is Vn, where n is the number of people also consuming the good. Imagine this can be supplied through constant returns to scale technology. So the supply curve is a flat line at the price equals average cost. Assuming that price is 1800, what equilibria are possible? All right, so first we need to build our ordinary demand curve. We can represent this as an ordinary demand curve with 200 people and a maximum willingness to pay of 100. That's this. Wait a second, where'd that come from? Well, we are told we have 200 people. Remember, on our horizontal axis, we're putting like our number of people in the market. It's like the size of the market. So that's going to be our horizontal intercept. The vertical intercept is corresponding to willingness to pay, the maximal reservation price, that's $100. So if we're drawing our inverse demand curve, the vertical intercept has to be 100 because that's my maximal reservation price. And I need the size of the market to be large enough to get 200 people into the market, which tells me my horizontal intercept has to be 200, so the slope has to be 1/2, right? Because if price is equal to 0, we have 1/2 n is equal to 100 or n is equal to 200, right? So that's where this is coming from. Suppose we only had 100 people with these same reservation prices, then my demand curve would be price is equal to 100 minus n. We'd only need a slope of 1 to put 100 people on the demand curve. But we have 200 people, so with maximal reservation price of 100, we need a slope of 1/2 to put 100 people onto that uniformly distributed demand curve. All right, this is network demand, so we have to capture that network externality. So it's going to be n times this reservation price. So it's going to be 100n minus 1/2 n squared. That is just going back to what we developed with network demand. That's going back to this structure right here. Okay. Maybe I shouldn't have done that. We're looking for 2 points where this downward opening parabola crosses marginal cost of 1800. So we get the following quadratic equation, which you can factor, or you can use the quadratic formula. But we need to solve this for the zeros of this quadratic. The zeros of this thing are going to correspond to where the demand curve crosses our supply curve, which is horizontal at 1800. So if I go to the quadratic formula, remember the quadratic formula is going to be b plus or minus b squared minus b plus or minus the square root of b squared minus 4ac divided by 2a. And you always kind of forget that this is 2a, right? So a was 1/2, Negative b, so b was 100, so negative b becomes positive 100. 4ac is going to be 4 times 1/2 times 1800. Okay. And so then what we're going to do is this is going to simplify really nicely. This is going to be 10,000 minus 3,600 is 6,400. And so solving out, we get 2 zeros of this equation. N is equal to 20 and n is equal to 180. So these are our two network sizes. We have the 0 network, we have the small network of 20, we have the large network of 180. And that's what we have found. All right, so here's another example. So you can think about this. Remember how many solutions there are to the quadratic formula, right? If the value under the radical is negative, there's 0 solutions. If it's 0, there's 1 solution. If it's positive, there's 2 solutions. Okay. So suppose we have 200 people in a market. Their reservation prices are between 1 and 100. Okay, everything's the same actually up to these average costs, $52.50. Oh, I gave us higher average costs. What's this going to do? You can check. This is otherwise the same problem, same setup. Assume my horizontal average cost is going to be $52.50. What equilibria are possible? Well, we need our demand curve. We've got this again. This is the demand curve. We capture the network externality. So the same as before. Basically, the only difference between this example and the previous one is we've raised our average cost. Now we got to factor this polynomial. We'll go to our quadratic formula so I can show what's happening here though. Here, what's going to happen? Oh, if we solve out, we've got 10,000 minus, I don't know what that was, 10,000 minus 1050, and that gives me minus 500. Well, that's not going to happen. There's going to be 0 solutions. So there's no zeros to this polynomial. Only the 0 network is possible. What's happened? Well, the costs of the good are too large. What would happen if the good was given away for free? What would we have? Suppose we gave away 100 units. Would that be stable? Well, that's something to think about. But here we have a situation where the costs are just costs are too high. Matter of fact, here we have the cost going right over the top of the. You can think about graphically here. The horizontal costs are going right. There's no intersection between our demand curve and the cost curve. All right, the last thing I want to do is I want to think about this game theory application. We can study network effects using game theory. So suppose we have two groups of consumers, row and column. NC is the number in the column group, NR is the number in the row group. And we could represent our total number of consumers by the sum of row and column, which is N. All right, we'll assume each group has the opportunity to adopt a new product or not, and is therefore faced with the choice to adopt or not. Players that decline to adopt receive a reservation utility of 0, standard. Players that adopt receive utility dependent on the behavior of the other player. So there's network effects when my utility for the network as a whole is bigger than my utility for just me for these consumers, right? So network effects are strong when the players are preferring to coordinate, right? When I have higher utility if both of us are in the network than if it's just me. So that gives rise to this structure. So if nobody joins, our reservation utilities are just 0. If I adopt as a row player, but they don't adopt, my utility is just the utility associated with being the only one on the network. If I don't adopt, but column player does, their utility is just whatever they get for being the only player in the network. If we both adopt, then our utility is going to be whatever it is for having both of us be on the network. Given that we're assuming there's this network effect, which is positive, and given that we're assuming that we'd rather not be the only one to have adopted, we'll make that negative. Now we get two equilibria, one where everyone adopts right here and one where no one adopts, right? Because if this is negative, then my best response when they don't adopt, my best response is to not adopt, right? If column player does not adopt, my payoff is 0, their payoff is 0 if I don't adopt. But if I do adopt and my payoff is negative and their payoff is 0, well, I'd rather avoid this negative payoff by adopting when they haven't adopted, and so we'll both not adopt. However, if I get a positive payoff for adopting when they adopt and a 0 payoff for not adopting when they adopt, as a row player, I want to adopt. What about for them? If they get a 0 payoff for not adopting when I don't adopt, but they get a negative payoff for adopting, they're not going to adopt. That reinforced that equilibrium. But if I do adopt and they get a zero, the column player gets a zero payoff for not adopting, but a positive payoff for adopting, they will adopt. So that reinforces this equilibrium. When does adoption occur? Each must expect the other player to adopt as well, and that's when they'll both adopt whatever is this network technology. All right, the last thing is just thinking about applications. So this was historic example. Thinking about the application to Bitcoin. So we discussed the demand curve for a network good, showed multiple equilibria could arise. Use this model to present a similar characterization and analysis of the following situation. Bitcoin, virtual currency, has been rising usage over the past 4 years or so. Well, now it's falling. It's highly decentralized, but can both be traded on exchanges or used privately. Suppose upon graduating, you are offered a wonderful job, but your prospective employer insists on paying your otherwise lucrative salary in Bitcoin. Will you accept the offer? Well, this ultimately comes down to a belief about your expectation of the size of the network. Currencies are network goods. And if you believe the network is going to be huge, then maybe you'd be willing to accept the offer. If you do not believe the network is going to be big, then you don't accept the offer unless you have some way to really quickly exchange your salary in Bitcoin for dollars or euros or whatever you want it in. The other thing is, like, when I was teaching at Carnegie Mellon in the early, was the 2013, 2014, I had a lot of Bitcoin examples, and Bitcoin price was really, really low, and I had all these Bitcoin examples, and I talked about it all the time, and I never had any Bitcoin of my own. And then, of course, Bitcoin price went to like 20,000, and I think now it's around like 10,000 or so. And if I had bought Bitcoin when I was teaching for Carnegie Mellon right out of grad school, I would not currently be teaching now. But I didn't, obviously. So anyway, and now it's not a very, I don't think there's any, I think the opportunity cost of buying any type of cryptocurrency is far too high relative to other things a person could put their money into. So not investment advice, however, wise economic counsel. So, all right, hope you enjoyed the video.